Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the IIT JAM exam held in 2025. And in this video, we discuss the solution of a problem related to group homomorphisms. This problem is suggested for the aspirants of CSIR National Eligibility Test and all set examinations. Right. The given question is, let R by Z denote the quotient group where Z is considered as a subgroup of the additive group of real numbers R. R is the additive group of real numbers and Z plus is a subgroup of R plus. Then R by Z is the quotient group. Let M denote the number of injective, we mean to say 1-to-1 group homomorphisms from Z3 to R by Z. And N denote the number of group homomorphisms from R by Z to Z3. Z modulo 3. Right. Then, which one of the following is true? We are given 4 options. Option A, M is equal to 2 and N is equal to 1. Likewise, options are given in B, C and D. Right. Let's now discuss the solution of the problem in detail. We have the quotient group R by Z. We will now discuss the injective group homomorphisms from Z3 to R by Z and we also count them. Given M is the number of injective group homomorphisms from Z3 to R by Z. Let phi be a map from Z3 to R by Z be an injective group homomorphism. Note that Z3 is a cyclic group of order 3 generated by 1. Since phi is an injective group homomorphism, injectiveness is necessary here, phi of Z3 is a cyclic subgroup of order 3 in R by Z. Right. Let phi of Z3 is a cyclic subgroup of order 3 of R by Z. Let phi of Z3 is a cyclic subgroup generated by 3. Let the generator be Z plus A. It is generated by Z plus A, where A is a real number, A not equal to 0 and 3A belongs to Z. 3A belongs to Z. Why? Because it should be a cyclic subgroup order 3. Right. We claim phi of Z3, the image of Z3 in R by Z, is actually cyclic subgroup of order 3. That we will show it is the cyclic subgroup generated by Z plus 1 by 3. We do it in the next slide. Right. That's what our claim is. Let 3A is equal to K. A is a real number, A not equal to 0. 3A is equal to K. Let us say that is K, where K belongs to Z star. And K is not a multiple multiple, integer is not an integer multiple of 3. 3a, a belongs to R, 3a belongs to Z, 3a will be K. That K is, you take some element non-zero integer, and K is not a integer multiple of 3. That implies A is equal to K by 3, and you note down K is not an integer multiple of 3. So A is equal to K by 3. If K is an integer multiple of 3, K by 3 will be an integer, and that A will be an integer. But A is a real number. Right. If K is equal to 1, not an integer multiple of 3, then A will be equal to 1 by 3. Then the cyclic subgroup generated by Z plus A will be cyclic subgroup generated by Z plus 1 by 3. It generates how? Z plus 1 by 3 plus Z plus 1 by 3, that is Z plus 2 by 3. Z plus 1 by 3 plus Z plus 1 by 3 plus Z plus 1 by 3 is Z. It is actually Z plus 1, Z plus 1 is Z only. So it is a cyclic subgroup generated by Z plus 2 by 3 also, because that is also a generator. Right. Right. For any K belongs to Z star, K is not an integer multiple of 3, then we get the cyclic subgroup generated by Z plus A will be equal to Z plus 1 by 3. This is what we want. So for any K belongs to Z star, K is not a integer multiple of 3. The cyclic subgroup generated by Z plus A is precisely the cyclic subgroup generated by Z plus 1 by 3. That is, A is 1 by 3, you can take it. This is what our claim is. Right. For example, K is equal to minus 7, which is not an integer multiple of 3. Then A will be K by 3, that is minus 7 by 3. And that is minus 3 plus 2 by 3, correct? Now, the cyclic subgroup generated by Z plus A will be equal to the cyclic subgroup generated by Z plus minus 7 by 3, that is equal to generated by Z minus 3 plus 2 by 3. Z minus 3 is Z only. 3 is an integer. This is Z plus 2 by 3. So cyclic subgroup generated by Z plus 2 by 3 is same as Z plus the cyclic subgroup generated by Z plus 1 by 3. Correct. So that means when K is not a integer multiple of 3, it works. So thus Z plus 1 by 3 is the unique cyclic subgroup of order 3 in R by Z. Why? Because you said for any Z plus A, where A is equal to K by 3, where K is not an integer multiple of 3, that also generates the same group, Z plus 1 by 3. So Z plus 1 by 3 is a unique cyclic subgroup of order 3, where it will be in R by Z. It will be in R by Z. Now, the 1-1 homomorphisms from phi from Z3 to R by Z will now reduce to phi from Z3 to the cyclic subgroup generated by Z plus 1 by 3. Both are cyclic groups. So, in the case of finite cyclic groups, a homomorphism maps a generator onto a generator. In Z3, generator is 1. In the cyclic group generated by Z plus 1 by 3, generators are Z plus 1 by 3 and Z plus 2 by 3. So what are the possibilities? Thus phi from Z3 to Z plus 1 by 3, a homomorphism, a one-to-one homomorphism, we have already one-to-oneness, has two choices. That is, one mapping to Z plus 1 by 3, one mapping to Z plus 2 by 3. Thus we have two injective homomorphisms. So M, the number of injective group homomorphisms from Z3 to R by Z is equal to 2. Right? Is equal to 2. So M is equal to 2. We continue the discussion for N, the number of homomorphisms from R by Z to Z by 3. Group homomorphisms from R by Z to Z by 3. Z3. Given N is equal to the number of group homomorphisms, not injective homomorphisms, just group homomorphisms from R by Z to Z3. Let phi be a map from R by Z to Z3 be a group homomorphism. We always have a trivial homomorphism. That means phi sending every element of R by Z to the 0 element of Z3. That is phi of Z plus R is equal to 0 for all Z plus R belongs to R by Z, R belongs to R. So, such a thing is called a trivial homomorphism. Now we have a question, is there any non-trivial homomorphism? Assume that psi from R by Z to Z3 be a non-trivial homomorphism. Meaning what? Meaning what? At least there will be one element in R by Z which is not mapped to 0. If every element maps to 0, it's a trivial homomorphism. So it's non-trivial, therefore there will be at least. Then there exists Z plus R belongs to R by Z such that psi of Z plus R is not equal to 0 for some R belongs to R star. Agreed. Now, psi of Z plus R can be written as psi of Z plus R by 3 plus R by 3 plus R by 3. But what is psi? Psi is a group homomorphism. Therefore, it will be psi of Z plus R by 3 plus psi of Z plus R by 3 plus psi of Z plus R by 3. What is this? This is 3 times psi of Z plus R by 3. Where is Z plus R by 3? It is an element of Z3. In Z3, 3 times an element is 0 because it's under addition modulo 3. So 3 times psi of Z plus R by 3 in Z3 is 0 because psi of Z plus R by 3 belongs to an element of Z3, is an element of Z3. So that means this means psi of Z plus R is equal to 0. But we have chosen such. We got by assumption that there exists an element Z plus R belongs to R by Z such that psi of Z plus R is not equal to 0. But now you are getting psi of Z plus R is equal to 0. This contradicts that it is not equal to 0. This contradiction tells you that your assumption is not true. Therefore, there are no non-trivial homomorphisms. That means there is only one trivial homomorphism. This shows that there are no non-trivial homomorphisms. Thus, trivial homomorphism is the only homomorphism. Therefore, N, the number of group homomorphisms from R by Z to Z3 is 1. We have already seen M is equal to 2. M is equal to 2. So let's now call on the options. So the option A says M is 2, N is equal to 1. Right. That's what precisely we got. So the answer to this question, so option A is true. The answer to this question is option A. And that is the detailed discussion of the solution of this problem from group theory related to group homomorphisms. Right. In my opinion, it is a good question, and that is why I am telling it is an important question even for that CSIR net aspirants also, and for also set examinations. Right. And nowadays, questions on homomorphisms, how many of them are there, are frequently coming. Therefore, work out such similar problems. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will certainly meet you all once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.